Hello. In this video, we're going to talk about the operation of the differential amplifier, the MOSFET differential amplifier, when we connect an active load. And an active load is basically a transistor current source that is replacing the drain resistors. Generally speaking, that is connected in place of a resistive load. But in this case, we can see that I have included my current source formed by PMOS transistors M3 and M4, and I've connected that in place of my drain resistors RD on each branch. And let's see how that affects the performance of the circuit. For one thing, DC-wise, not much has changed. We have the tail current I, and under balanced conditions, meaning same signals applied at the gates of both transistors, VG1 and VG2, we're going to have that current split between the two branches, and so we're going to have I halves current flowing through each branch. Since the current going into the gates of a MOSFET transistor is 0, I'm going to have 0 current flowing through that branch that joins the drain and the gate of transistor M3, which is the diode connected transistor, and I'm going to have also I halves flowing through M3 and M4. Right? Notice that my current I halves that I'm forcing through M3 and M4 is going to produce a source to gate voltage, VSG. I'm going to call that my VSG3. Just to keep things positive, otherwise it could be a negative value of VGS. So that my output voltage, if things are balanced, I'm going to have symmetry between the two branches. So my output voltage, DC-wise, before I apply any small signal, should be equal to PVD minus VSG3. And I probably should indicate DC signal by making this a capital. Okay, and that's just going to be the offset or the DC bias point of my output voltage. As I apply a small signal, what I have is variations or fluctuations in the currents and voltages around the quiescent point, around the Q point. We have seen, for example, if I increase the value of VG1 slightly, I apply a small VG1 signal of VID halves. For example, what I have is that my current through branch number 1, the one with the M1 transistor, increases, and the current through the other branch decreases, which is going to cause a temporary increase in that output voltage or decrease if my signal goes in the opposite direction. Let's take a look at what the gain would be. Small signal equivalent circuit. And this is basically what I have. I'm going to turn off my DC sources. Here is my diode connected transistor M3. Sometimes it just appears as a diode, and that's fine. So sometimes you'll see it connected like as follows. And notice, since this is the drain of M3 is connected to the gate, and it's also connected to the other transistor. So this is what you may see it as appear as in the connection, and this is exactly the same thing. This is an active load, okay, equivalently or electrically equivalent to the previous case. Let me just draw it the same as before. All right, so that's for my M3 and M4, my PMOS transistors. And then I will have my M1 and M2, which are my NMOSes. And basically in my small signal equivalent, my DC current source will be an open circuit, so this will also be sitting at ground or 0 volts. Let's be the G1, which is VID halves, and this is VG2, which is negative VID halves, so the small signal, if you remember. All right, and what I am going to have with my small signal circuit is, if you recall, as we previously did, I'm going to have, since I have an increase or a small signal input voltage VID halves on the gate of M1, that's going to produce a current here, which is going to be GM VID halves, right? It's going to produce a current in the opposite direction, GM VID halves. Since it is negative. But then notice that because of the effect of the current mirror at the top, right, the current through M3 is going to be equal to GM VID halves, the small signal current. And because M4 is a current mirror, it's going to have the same, any change that you apply on transistor M3 is going to be reproduced in transistor M4. So the small signal current is also going to be GM VID halves, that's flowing downwards, so that at my output node, the overall current there is going to be 2 times a small ID. Okay. Now, what that means is, if you remember, notice that I have drawn my amplifier with a single-ended output, and that will be the only possibility for a DFAM that has an active load, because notice that the other output, the drain of M1, which is also the drain of M3, that one is tied. That one is tied to VSG3, right? And therefore, we can only take the single-ended output. But in the single-ended output DFAM with drain resistors, we had that the differential gain was 1/2 of GM times RD. In this case, though, I could draw, if I were to draw like that output stage in my small signal equivalent, you should see that I can represent M4 as a signal source, right, which is flowing away from ground. So if ground is down here, the current is flowing away from ground. It's going to be GM VID over 2. And then we haven't represented that, but the only place that it can typically flow, since if we connect the DFAM to the gate of another MOSFET transistor, the current going into the gate is going to be equal to 0. And so the current is going to flow through the output resistances of these transistors. And this will be Rout 4. Or if I wanted to represent it in my figure up there, I guess we haven't done that, but we did something like that, right? This will be Rout 4. This will be Rout 2. So they're connected between the output node and the ground, both of them. And my M2 transistor can be represented as a current source, which is also flowing away from ground. And so I could represent it as a current source in parallel with this one. GM VID over 2. And its associated output resistance is Rout 2. And this will be the output node right here. Okay. And so my gain, which will be my single-ended output with active load. My differential gain, which will be V out over VID, will be equal to, and notice that the current that develops here, or the voltage that develops, is going to be the current times the resistance. Therefore, it's going to be GM, let's see, this is over VID, and this is going to be, the current is 2 times GM VID halves times the resistance, which is Rout 2 in parallel with Rout 4. And so my 2's are going to cancel, and my VIDs are going to cancel, and so my gain is going to be GM Rout 2 in parallel with Rout 4. And that's an important result, because notice it will be what we will expect from a balanced output, right? The differential gain will be negative, but GM in absolute terms, it will be GM times the resistance connected at the drain. We typically approximate it as RD, but it should be RD in parallel with little RO, right? In this case, RD has been replaced with transistor M4, and therefore the output resistance there is little RO4. And so the result that I'm getting for the single-ended output is, I've gotten rid of that 1/2 term. It's not 1/2 of GM times the output resistance, but rather GM times the output resistance. And that's because of the effect of the current source. So note number 1, note, I can convert signal to single-ended without loss of gain, loss in gain. And remember that the loss was actually, we were getting 1/2, so it's a loss of 50%. It was a large loss. So that's one of the advantages. So perhaps I should list, advantages. That will be one of them. Can convert the signal to single-ended without loss of gain. Because that's my new differential gain now. And that's just because I have essentially increased my output resistance. My output resistance now is going to be, that's not what I intended to do. This is due to increase R out, where R out is equal to R out 2 in parallel with R out 4. Okay. Now, the higher R out actually is going to give us an improvement in CMRR. So, higher R out, this leads to increased gain, as we have mentioned, and that increased differential gain, and that leads to an improved CMRR. So in essence, a lot of improvement in performance by using the active load. Now, obviously, if we were able to keep increasing R out, right now we are limited, our R out resistance is little RO2 in parallel with little R out 4. If we keep increasing our R out, our performance is going to get even better in terms of gain, which it tends to be a concern with MOSFET transistors. They tend to have GMs or transconductance parameters that are lower, inherently lower than BJT transistors. And so one solution or one possibility of circuit to keep increasing the output resistance. So I can say we can further increase our out by using the Cascode configuration. And if you remember the Cascode configuration, when we talked about current sources, the output resistance of a Cascode, it basically increased the output resistance from little RO, it multiplied it by a factor of GM times little RO approximately. More precisely, 1 plus GM times little RO. Now we can apply that here as well to increase our output resistance and thus increase our gain. And so we have, we can have a MOSFET diff amp with a Cascode active load. And what we're basically doing there is we're taking our diff amp as is, but then in the Cascode, or in the active load, excuse me, we're just gonna connect it in Cascode configuration. Higher transistor count, but higher gain as well. And as we know in electronics, you rarely ever get anything without a trade-off. So in the case of the Cascode, these two will be diode connected. And then I will have my differential pair. Minus VSS, this will be VDD, M1, M2, M3, M4, M5, and M6. Right, and so basically my output voltage will be taken here, and notice that I have the output resistance looking down here, it will be little RO2. The output resistance looking there, we can call it capital RO, will be approximately equal, I'm going to say equal to ROut4 times 1 plus GM little RO6, but approximately equal to ROut4 or GM ROut4 ROut6. Okay, and therefore my gain for the circuit will become now GM times ROut2 in parallel with GM ROut4 ROut6. What is the improvement? Well, the improvement is before I used to have GM ROut2 in parallel with ROut4, so it's basically 1/2 of GM times little RO. Whereas right now I've basically doubled it. It's GM ROut2, and hopefully that second term GM ROut4 ROut6 will be much larger than ROut2. And so this parallel combination is approximately equal to ROut2. And so basically I've sort of doubled my gain with respect to the simple circuit with a simple active load. I can take things even one step further and implement MOSFET Cascode diff amp with a Cascode active load. And as the name implies, and I'm going to, sorry, I'll find differently. I'm going to, for simplicity, just represent M5 and M3, that like the two diode connected transistors as diodes. And I hope that doesn't confuse anybody. They're electrically equivalent connections. Nothing has changed on the top part with respect to the previous example. The only thing that I'm changing is making life simpler for myself, I suppose. All right, so notice that those are still the same because, again, the drain of M5 is connected to the gate of M6, and so those are the connections that we have here, essentially. These are still diode-connected transistors, so if you look, if you go inside the circuit, this will be a transistor connected in that fashion of connecting the gate to the drain. And then we will have two NMOS transistors. They will require some kind of bias voltage. Make sure that they are turned on. And finally, minus VSS. This is my current I, VG1, VG2. And so this will be M1, M2, M3, M4, M5, M6, M7, and M8. And essentially what I will have here is I will take my output right there. And so my, because of the Cascode effect, I will have here my R out, I'll call it 4 because I'm looking into M4, and my R out 6. But essentially, this one will be equal to little r out 4 multiplied times 1 plus gm r out 2. So approximately equal to gm r out 2 r out 4. And r out 6 will be equal to r out 6, little r out 6, 1 plus gm r out 8. And so approximately equal to gm r out 6 r out 8. So when I go to calculate my gain now, it's going to be equal to gm times the equivalent resistance. And again, one could consider a load resistance, but if we are driving this into the gate of another transistor, it's virtually an infinite input impedance. And so what remains is just the output resistances of the different transistors on this stage, which basically would be gm r out 2, r out 4 in parallel with gm r out 6, r out 8. And so we've basically increased our gain drastically from the previous example by a factor of gm times little r. So these are some of the techniques in order to achieve higher gains with MOSFET differential amplifiers, which is something that we typically want when we're designing, for example, op-amp circuits. We're going to want an amplifier that has a very high gain. We don't have a lot of control over the gain with the active load. That is true because it depends on output resistances and things like that. Not of a nice drain resistor that we can select the value for very cleanly. But again, when we're designing op-amp circuits, we're not going to care so much about the accurate value of the gain, but rather the fact that the gain is really high. We want it to be as high as possible because the idea is that then we're going to connect the amplifier using negative feedback, and we're going to decrease the gain, make it virtually independent of the open loop gain and mostly dependent on external components. But in order for that approximation, that independence of the open loop gain to be close to reality, we need for the gain to be as high as possible. And that's why we care about building an amplifier with a very high gain as opposed to a very accurate gain. Thank you.